Hi, I'm Marcus Schaefer. In today's video, I'm going to discuss how Big O, the math behind it, can be solved using integration and limits. First off, I'm going to give you a little scenario. Imagine you are a computer science major and you've been tasked to program a searching algorithm for a phone book with, let's say, 100,000 residents in this town. Now, one could easily look up on the internet, what is the best searching algorithm for this? And the answer you would most likely get would be a log n searching algorithm. But a log n searching algorithm. Sorry. But why is it log n? And how did your sources that you used come to this conclusion? Well, first off, it's because the calculus used behind the scenes has proven that log n is the best searching algorithm. Like a function with a searching algorithm, a big O of log n is good. But what does that all mean? Like, why is it good? Like, what is the math behind the scenes? And that today is what I will show you. First, I'm going to go into a little bit detail about what big O is. I'll discuss what limits are. I'll go over integration. I will explain how they are tied together, and I'll also explain how you can use limits and integration to solve for certain searching algorithms, and their big O, and their worst case, their big O, their time complexity, and show the math behind the scenes as to how your sources came to that conclusion. First, what is big O? Big O is an upper bound. Well, it's a big O and time complexity go not hand in hand, but really, really close. Big O is the upper bound of a function, of an asymptotic function. It's a notation used to describe the worst case scenario of a function's time complexity. Time complexity is described as an algorithm's time it takes to run operations. So, for example, if I had a function that featured printing out the words hello, alright, this is in C++, by the way. So, this function has a big O, a worst case scenario of 1, because it can only run one time. It's only hitting this operation once, so it's an O, a big O, of 1. Now, what if we were to stick a for loop? So we add this for loop, which do while I is less than 10, I plus plus, I equals 0. We're just going to do that. Now, it's no longer O1 because we incorporated this loop right here. See? With this loop right here, now we're hitting this operation 10 times, meaning that it's now an operation, a big O of O n, because n is some unknown number. This operation could hit once, it could hit 10 times, 100 times, 1,000,000 times. We don't know, which is why it has a worst case scenario of O n. Big O is used to figure out the best way to sort something or search something. It tells us what algorithms have the best time complexity given a certain amount of elements and the number of operations. So here's a graph that will help demonstrate what's going on with Big O. So I'm going to put this over here. So we have this graph. We have the number of elements, number of operations. Now, I will use x squared as an example. So x squared is parabola, as we know. It looks something like this. But I'm going to call it n squared, just for Big O's sake. I can see that. I'm going to go n squared. There you go. So, knowing this, erase that down a little bit so you can see where the arrow is. Boop, that's n squared. Okay. Now, given the number of elements, it'll give us some number of operations. And this is what this graph will tell us, is it'll tell us what functions give us the least amount of operations given a bunch of elements. So as this element, let's say this is 5. 5 squared is 25. So we've already done 25 operations. But if we incorporate, this will be log of x, if you incorporate 5, that's a number that's less than 1, which that's less than 1 operation, meaning that there's not a lot of operations in a log x function. And that's what big O shows. Big O is the worst case scenario, and this graph is explaining that worst case scenario, and in terms of time complexity, if that makes sense. It's explaining that given this time complexity of, given this like certain number of elements, how long will the algorithm run? That's what time complexity does, and this is what this graph is showing. Now I'm going to explain limits and how limits are, what limits are, what limits show, and what limits mean. So a limit is a tendency. So I'll use this graph over here. So we have this graph. We're going to do good old Mr. Parabola. Okay. This will be x squared. Okay. Now we have this graph, but like we don't know much about it. We just know it's x squared. We can use limits to define things about our graph. These will tell us things of what's going on of x squared. So what I just described right here, what I did was I mounted this to a limit problem. I'm saying as x goes off to infinity, I'm going to use the right side of the graph, what is x tending towards? So, a good visualization for this is a little character. He's going this way. He's going up this curve. He's going off to this. He's going up this hill, and he's going off somewhere. Where is he going? Well, he's obviously going to infinity. But how fast is he getting there? Or how fast is x squared going to infinity? Another thing limits can tell is speed. So, given our x squared and having our f of x here, we can find specific values. So we can use 1, 2, 10, 20. Given this, we can go, we know that if we plug it into x squared, the return values are 1, 4, 100, and 400. Limits show how the speed of which something is going off to infinity. We know it's going to infinity, but we can use this table and we know where the limit's tending towards to show that it's really, really fast. We can use other graphs that depict the speed of it as well. We can use a log x, for example, to show how fast it gets there. But that is what limits show. Limits themselves are limits are tendencies. Where is the graph tending toward? Or what is happening at this point, and where is it tending towards? That's the best way to describe a limit. I'm going to keep this table up here. Limits are tendencies. When the graph is tending towards something, that is how you really describe a limit. It's going off towards infinity, or it's tending towards infinity. Now, I'm going to switch gears and go to integrals. Integrals are used to calculate the area underneath a curve. This can be done by 2 ways. So, you can use Riemann sums, which calculates subintervals, and it can be over or under estimate depending on the curve and the Riemann sum you choose. Or you can use integration, and we're going to use integration. There's also 2 types of integration, definite and indefinite. The difference between the two is one has bounds and one doesn't, and that does affect the overall integration itself. Now, we're going to integrate x squared. So we're going to do between 2 and 5. This dx right here is important because dx tells us that we're doing an integration. So the integration of this is going to be 1/3 x cubed between the bounds of 2 and 5. So we're using this integration to calculate between 2 points. So I'm going to draw out a graph real quick. So let's say this is our line. So between here and here, so like this is like 2, this is 5. It's obviously not a parabola, but what is this area down here? That is what we are doing with this line. We are not using exactly that value. We're doing x squared, which is a parabola, but same principle. It's the area underneath the curve between 2 points. And some curves aren't as nice as that. Sometimes they're super wavy, like a sine curve. It's really hard to calculate the area against something that isn't a flat, where it's more wavy. This is where integration comes in, and as well as Riemann sums as well. So we go through. We're doing 5 times 5 is 25. 25 times 5. 125. So this will be 125 over 3 minus 2, 4, 8, 8/3, which is equal to I got something on there real quick. What's that? 117? 117. So that would be the area under the curve between 2 and 5 for an x squared function. Now we can look at this for log of x as well, which is our other function. So we can do the same thing. Log of x dx, which translates to x times log of x minus 1 to 2 and 5. You plug these in, so we're going to get 5 log of 4 minus, now log of 2 minus 1 is 1, and log of 1 is 0. This is minus 0. So to make this quick, it's going to be minus 0, and this is our answer. Now, integration limits are very, very different. So where's the comparison here? Well, there's a really big comparison. You can run the limit of since the integrals are a sum, you can do the limit of a sum, and it will get you this same answer. So if you do the limit of a sum, when you use Riemann sums, as your number of subintervals goes off to infinity, you're doing the sum of f of whatever, f of 1 plus b minus a over n. We're going to do, I'm missing a b minus a over n outside, k, with b and a are arbitrary numbers. N stays the same. It doesn't change. You keep n as it is. And as we go through this, depending on your number of subintervals, or depending on whatever your function is, you will end up with either of these. This can be used to confirm what the integrations show us. That's how they connect. You can use the limit of an interval, of an integration, to get this. You can use the limit of a sum, Riemann sums, to get the same thing as an integration, which is really, really cool. Just the mag. Something right. Okay. Now I'm going to relate this all back to big O. With with our limits, as we showed before, we're checking x squared. We've already checked the interval. We're going to check the area under the curve for this, and we know it's very different. This value is much bigger than that value. And we can go back up here as well. This will be, we can do the limit as for log of x, as x approaches infinity. for x, f of x, same values. I keep them the same. We're going to draw this line. So 1, 2, 10. I'm just going to this out. 20. Okay, I'm using my left hand by the way, so this is really hard. So we plug in our values for 1, for all these x, so we get 0.301. This is 1. This is 1.301. So, as I said before, we can use limits to track the speed of a value going off somewhere. So as soon as we hit 20 elements, we've only done 1.301 operations. But when we hit 20 elements of x squared, we've done 400 operations, which is really inefficient. And same down here as well. We did the area under the curve between two elements. This is off to infinity, mind you. So these numbers are only going to get bigger and bigger. Here, it's between two bounds. This is going to stay the same. Here, we have 5 log 4, which is somewhere between 1 and 0.301. Actually, no. It'd be whatever 4 log 4 is between these two, and then times 5. I believe it's approximately 3. I could be wrong. I'm going to double check on my calculator. So 5 log 4. It's about 3.01. 117 divided by 3 is 39. So, very, very different numbers. This is 39. This is 3 and change. That's a big difference because it shows how long it would take to calculate for an array of between a value elements of 2 to 5, and it takes 39, whatever, right? The time complexity is 39. Time complexity of this is 3. Imagine if it was 100,000. Now I relate back to the example. This is why log n is better, would be your preferred answer than anything else, because you are going to deal with a big database with all these 100,000 people in it. Now, here in this curve, we can see that, let's say 100,000 was right here. Let's say 100,000 out here. Well, 100,000 squared is 5 zeros, it'd be 10 zeros. That's a big number. Log of 100,000 would end up being, I don't even know, 5. So, with there being 100,000 operations, this would be, I'm not going to do that, it would be just, I can do that real quick, it would be log of n equals, this would be 5, with n being 100,000, this would be 1, so double, be 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 6, 9, 10. So it'd be 10 million. Hundreds, thousands, millions, 100,000, 10 billion. Sorry, 10 billion operations would have been done on you can see my face, on a database of 100,000 people if you're searching for somebody using n squared. N, it'd be 100,000. Now, as I've shown, this is how you would prove what your sources are telling you. You can use limits. It uses limits to show how fast it gets to infinity, which helps us show that as the elements keep expanding, and we keep pouring onto this database, like let's say 50,000 more people move in. Well, that's more operations you're going to have to run if you're using a search like n squared. If you're using a search like log n, you're only going to run maybe 6, I don't know. Whatever log base, this would be that
let's say 50,000 more people show up. So it's 100,000, so 5. So
A little bit, it's like 5.2. You'd be running a little bit more than 5 operations to find who you're looking for. That's the reason why log n is going to be your source is solution. Because the more elements you pile on, the least amount of operations we want to keep it at, which helps us save memory. We don't have to keep repeating the same thing over and over again. And that is why your source will give you that information. Now, overall, this is the math behind the scenes of Big O. Limits check the speed of which a function will go off to infinity, and integration will check the distance, it will check the area under the curve to see which one, to see the time complexity of which function. I hope you enjoyed the video, and I hope you learned something. This video will be linked in my essay as well. And I hope you have a great day. God bless, and go Ravens.